Welcome to the next video in a course in real analysis. We're still discussing lesson 2, rings and fields. This is the solutions video for the exercises introduced in the previous video. So let's start by recalling the first exercise, and that was to show that the singleton set of 0 is a ring. And to show that something is a ring, we just need to step through all of the conditions. And so to begin with, we need to know that the set is non-empty. Of course, since this set has 0, it is non-empty. Now, next we need to know about the operation, and we don't even have the operation given explicitly. As I said in the, when I was introducing these exercises, I won't tell you the operation, but there's only one possible. And so what is that operation? Well, it is essentially given by this here, and this is essentially sending the input pair 0, 0 over to the element 0. Well, there's only one element in the domain for, f cross f, which is this one pair where each coordinate is filled with 0. In order to make this an operation, there's only one thing we could possibly send it to, which is 0, the only thing in the set. So that's the only operation possible on a singleton set, binary operation. And so that must be what plus is, and it also must be what times is. Now, we will want to know for the rest of this that this operation is associative, and that's very easy to demonstrate. So you simply have to write down every possible triple, but there's just this one triple, 0, 0, 0. Write its parentheses in one way, compute, so that's going to be 0 plus 0, and then that further computes to 0. Write the parenthesization in the other way, compute, see that you get the same result. And since this looks at every possible triple, then we have confirmed associativity. So let's next go ahead and look at the remaining conditions that we have to confirm to show that this is a ring. Now, we need to know that when we restrict to the plus operation, we get a commutative group. I should have written that here, so I do need to specify that this needs to be a commutative group. Now, to show that it is any kind of group at all, then we need to know that the operation is associative, but we just confirmed that. We also need to know that it has an identity element. Now, it is trivial to confirm that 0 acts as an additive identity, since, of course, if you do 0 plus 0, you get 0. We've already said that. And so it means that if you take anything, right, like let's just go ahead and say that that is x, right? And we know that that results in x always, because in both cases, the only thing that x could possibly be is 0. And so for all x in this set, 0 acts as an identity. And so that is it. It has an identity. The identity is 0. And then we need to check that everything has an inverse element. Well, since the only thing here is 0, and again, since 0 plus 0 is 0, then 0 is its own inverse element, which is in fact completely typical, right? In every group, the 0 element is its own inverse element. But that's it, right? Because since that's the only thing to check, then every element has an inverse. So this, in fact, is a group. To check commutativity, we would need to know that if you wrote anything plus anything, and then wrote it in reverse. Well, again, right, this is all very trivial because there is only one element. But so this essentially is what you have to check that it's commutative. But since clearly that's true because both of these are equal to 0, then it is a commutative group. Okay. So there we have it, right? So when we restrict to the plus operation, it is a commutative group. Let's move on to talking about the conditions for the multiplication operation. Well, we need to know that it's associative. We've already checked that. We need to know that it has an identity element. Again, that is 0, just as it was for the plus operation. The identity is also 0 for the times operation because they're the same operation. Anyway, that's that. Now we finally have to check that times distributes over plus. And so technically what you have to do is write down the distributive equation, I guess you could call it, for every possible triple. Again, right, this is all very trivial because there's just one possible triple. That would be 0, 0, 0. But you write it down like this: compute, get that the result is 0. You also have to check that you get the same thing if you wrote what, basically it is supposed to come out to according to distributivity. But again, that's going to be 0 plus 0, right? Computing that 0 times 0 is 0. And so you do that twice and you get 0 plus 0. And again, that turns into 0. Since you got the same thing, then you've confirmed the equation that is necessary for this triple, and since it's the only triple possible, then this is everything, right? That confirms it for every triple of elements. And so times does distribute over plus in this example, and there you have it. We've met every condition for this to be a ring. So the exercise is complete.
So let's move on now to problem number 2, where we're going to show that in any group, the identity element is unique. Now, as I described in the previous video, what that means, especially for the proof, is that we're going to let some other element, here we'll call it x, be some element of the group with the identity property, which is to say, let's go ahead and write out what that means, right? The identity property says that for all elements of the group, then multiplying, so to speak, using multiplication notation, multiplying x with anything leaves it alone. So you can think of it as x goes away or it leaves y alone. And so that's what it means for x to be an identity element. It's, so to speak, two-sided in the sense that it can either sort of act on the left or act on the right and still act like an identity element. And so we're going to suppose that this exists, and our goal then is to show that this x must equal E. Again, E is the element guaranteed by the axioms to exist and be an identity element, right? So we know E is an identity element. We're supposing that there's this other x, which also has the identity property. And then what we want to do is show that they must be equal to each other, showing that whenever you have anything that has the identity property, it is equal to E. That is to say, there is only one element with the identity property. So how are we going to show that x equals E? Well, let's consider, if you think about it, we just have these two elements. They're the only things that we know exist in the group. So we have to do something with each of them. And kind of the only thing you can do in a group is use the operation. So let's put them together in the operation and see what we can say about that. Now, since this has E, the identity element, then if we use the very property that defines it, then that means it can just go away. And so EX is equal to just X. So that's using the identity property of E. Let's next also use the identity property of X in the same expression.
And when we do that, we see that EX is also equal to E. And so if we sort of total everything that we have discovered so far, we earlier showed that EX is X, but now we've just shown that EX is also equal to E. So all three of these things must be equal to each other. And the part that we really care about is that X is equal to E, what we set out to show in the first place. And so the proof is now complete. Okay, let's move on to problem number 3, where we use what we just showed in problem number 2 to demonstrate that the identities in a ring, both the additive and the multiplicative identities, are unique. Now, when it comes to the additive identity, this is completely trivial because we know that when you restrict to the plus operation, you have a commutative group. The only thing that really matters there is that it is a group. We just proved that in any group, the identity is unique. So we know that in a ring, 0 must be unique as an immediate consequence of the previous problem. But then when it comes to the multiplicative identity, there is just a little bit of work. And the reason for that is that when you restrict to the multiplication operation, you don't necessarily get a group. And the previous exercise did talk about specifically when you're dealing with a group. Now, the way that the multiplication operation may not be a group is that it may lack inverses, right? The definition of a ring does not require that every element have an inverse. And so it may not, right, a ring may, when restricted to multiplication, we may not be working with a group, and so we don't satisfy the condition for appealing to this result. But if you look at the proof that we gave here, nothing here actually used inverse elements. So really that part of the assumption was not necessary. And so if you just repeat this proof all over again, but using the multiplicative identity 1 in place of E everywhere, then exactly the same proof works to show that the multiplicative identity is unique. And so I take it, I don't need to go back through all that. Just, now that you see that if you just replace it with 1, the exact same proof works. That is the proof that 1, the multiplicative identity, is unique in a ring. So moving on to problem number 4, we're going to show that 0 times anything is equal to 0. Now, I have not prepped this with a video thing. I kind of tacked this problem on at the end because like in a few, I was working on a video for later on in the playlist, and I needed basically this result, so I kind of came back and tacked on this exercise so that I would have it in a few, have the result in a future video. So I didn't prepare a video proof or solution, so I'm just going to do it by hand here. And so we're going to prove that 0x equals 0, and that's the only part of it I'm going to prove. I'm going to leave it to you to reproduce the same basic idea to show the same thing when it's flipped around. But so here I'm just going to show the left equation. And so I'm going to start from 0x. And as I hinted at in the previous video, the way that we're going to try to think about this is that, well, we're going to need to use the additive identity property somehow. And also because we're trying to see how it interacts with multiplication, and that's mainly, if not only, done with the distributive property, then somehow we're going to try to work the distributive property into this proof. Well, after playing around with things for a bit, maybe you realize that you could say that 0 is equal to 0 plus 0. That's using the identity, the additive identity property. And now it sets us up in the next move to do distribution. So we get 0x plus 0x. Now, where do we go from here? Well, you notice that on both sides of this equation, here and here, we have the same object. We kind of know that this object just is the number 0, but you have to resist using that fact in any way. So just pretending like we don't know what it is. Well, even if we don't know what it is, we do know that we can subtract it from both sides. And when I say subtract it from both sides, what I really mean is add its additive inverse so that there will be a cancellation, which I have done here. And clearly from here, we go ahead and use the additive inverse property. This simplifies on the left to 0, and on the right-hand side, by grouping things, perhaps using associativity to group a 0x together with a minus 0x. We can simplify that also to 0. And then for one further step on the right-hand side, we can say that this is equal to 0x. And then when you look at what we have now discovered, we have discovered that 0 equals 0x, which is exactly what we wanted to prove this whole time. So the proof is complete. So let's now move on to problem number 5, where we're going to prove that -1 times anything is equal to its additive inverse. And the way that we're going to approach this is to show that the right-hand side has the property that defines the additive inverse of x. Now, what is that property? Well, it's the property that if you take this thing and you add x, then we would like to show that this equals 0. That's the property of being the additive inverse. Once we show that this thing has that property, then it will follow that this thing is equal to the additive inverse. But I do want to mention that that really depends, right? That step in the argument where I say because it has the property, then it must be the additive inverse, depends on the uniqueness of additive inverses, kind of like the uniqueness of the identity that we proved in the previous step. Well, you also need the uniqueness of inverses. I have not proved that. You should feel encouraged to prove it yourself. It should be somewhat similar to the proof of the uniqueness of the identity, not perfectly similar, but you should go ahead and work on it and try to come up with your own proof for the uniqueness of inverses. And once you have it, then the argument that I make here is valid. But okay, so if we assume that we have that principle, we still need to figure out how am I going to show that this sum is equal to 0? And maybe what you think about or notice is that this has an x in each term, and that sure looks like the result of distribution. And so let's write a somewhat abstract formulation of distribution here. So a plus b times x is ax plus bx. That's distribution. Now, we're thinking maybe that this here that we have looks a little bit like the right-hand side of distribution. Definitely has 2 x's in it, so that's pretty good. But one, and by the way, if it's not already clear, what I'm thinking is that maybe we'll try to run distribution in reverse, right? There's nothing that stops us from doing that. An equation works both left to right and right to left. So, so can I use distribution in reverse, which we more commonly call factoring, by the way, but in any case, well, only if I can tell you what A is and what B is so that everything lines up. Clearly, we're going to say that A is the -1, but what is B going to be? Well, in order to make it completely explicit, let's go ahead and use the fact that the identity for multiplication must exist, and it is the number 1. So this must equal -1x plus 1x. There's our B. Right, so that's going to be B. Again, A is the -1. So I know that these are equal because I know that this just is the same thing as this because 1 is the multiplicative identity, which definitely exists by the axioms of a ring. So we get that these two things are equal to each other. Now distribution, I can tell you, what is A, what is B, and therefore we can use distribution. So this tells me that if I write A, again, we said that A is -1 plus, so I'm like following this formula here, A plus B. So that's A plus B, which we said was 1, times X, because that's what goes on the outside there. These must be equal, right? So we've got our next step. Now, where do we go from here? Here, I think it's pretty straightforward, right? -1 and 1 make 0 just by definition of additive inverses, so that's 0x. And here, magically, we have been set up so that we can use the previous result, which says that 0 times anything is equal to 0. And this is exactly the result that we wanted. So since we've shown that this thing has the property of the additive inverse of x, then since you have on your end proved the uniqueness of additive inverses, we can therefore, from the fact that it has this property, we can therefore say that -1x is -x. And there concludes the proof. Okay, we'll start talking about a new topic in the next video.